Hey everyone, so we are doing office hours right now. We've got a couple questions that we want to work on. Um, and so let's take a look at those real quick. We're going to be looking at 9.2, number 13. We're going to be looking at 8.1, number 10, and we're going to be looking at balancing reactions. I'm trying to make this recording so nobody's video is caught, but if you want to unmute and speak at any point, go ahead and do so. Otherwise, you can just put things in chat and we'll go from there. So I'm going to start with talking about balancing reactions, and then we'll look at how that kind of goes along with 8.1, number 10, and 9.2, number 13. And we'll kind of do it in context of 8.1, number 10 to see how it's going. But first off, whenever we're balancing a chemical reaction, I'm going to try to come up with a difficult one to balance. Let's do silver nitrate. This would be aqueous because all nitrate compounds are aqueous. I'm just making this up. So hopefully I make up a good one. Silver nitrate with let's do magnesium phosphate. And I don't know if this is a good one to do or not because, well, let me check something real quick. This is the problem with making up problems on the spot is I don't know if this is a good problem or not. Let me just check some solubility rules real quick. Phosphate. Nope, that's a bad one to do. Magnesium phosphate's not soluble. So let's just go ahead and do um, potassium phosphate. That one's aqueous. And then we can look at the chemical reaction. We can start predicting the chemical reaction and see what happens. 9.1, number 16, you got it. Okay, so we want to balance this chemical reaction. The first thing we have to do is predict products. I'm going to do my flip-flop, where I'm looking at my cation and my cation swapping places. So silver replaces potassium, potassium replaces silver. That's what we're looking at. So I do my flip-flop, and as a first kind of approach to it, I'm just going to put AgPO4. Got to figure out the state of matter there, and that's going to be plus KNO3. And I've got to figure out the state of matter there. Predicting correct products is kind of one of the most important things to making sure we balance the chemical reaction correctly. So I just do my flip-flop, and then I go and check my subscripts to make sure everything I made is reasonable. Sorry, it's not easy for me to do subscripts on Zoom meetings, so these are not subscript, but just imagine with me. So I've got the potassium, which is a +1. We'll do some kind of considerations. Silver is a +1, nitrate's a -1, potassium's a +1, phosphate is a -3, right? And this is from remembering my common polyatomic ions. So I can see I've got 3 of my +1s to balance that -3. Silver is a +1, phosphate is a -3. So I can see there, this compound is going to have problems. It's not currently charge balanced. Then I've got a +1 and a -1, so that one's looking good. Then I can go ahead and fix my compounds. In order to fix this one, I'm going to need 3 silvers there. I can already predict that this is aqueous because nitrate compounds are. Hopefully you're all muted and saying always aqueous right now. And now I've got that subscript 3 for the silver, which means that I'm going to have a nice charge balance on that as well. To figure out the solubility of that compound, I look at my solubility rules. These kind of ionic compounds here is phosphate. And you can see why I wanted to do magnesium phosphate to make it a little bit tricky, but magnesium phosphate would be a precipitate, and I wanted to do something that was soluble. So phosphates are soluble, but only with group 1, beginning with sodium on. So lithium phosphate would precipitate, but silver phosphate should form a precipitate. So we look at our problem here. This is going to be a precipitate. Okay, now in order to balance this, there's kind of two different levels. And Beverly, feel free to tell me if this is like too easy, I'm going too slow, or if you need more steps, just let me know. But I'm doing it like, since you just said balancing in general, I'm just doing like the full consideration. Now we kind of do some keeping track. And once we practice this a bit, we can really keep track in our heads. But what I'm going to check is I need the same atom number on my reactant side as my product side. So here I can see that I've got silver, I've got nitrate, I've got potassium, and I've got phosphate. Pardon my penmanship. Put some charges on these as well to help us keep track. Doing this with a trackpad. We're going to have the same atoms on the product side, right? We're going to have silver. We're going to have nitrate, potassium, and phosphate. Oof. Now, already on my product side, without doing any coefficients, I'm going to have 1, 1, 3, 1. On my product side, I've got 3, 1, 1, 1. And what I need to recognize is the fact that I need to change these numbers around without changing the subscripts, only changing the coefficients out front. So for example, if I put a 3 here, that's going to triple both of these. I can't do one or the other. I have to do both. But I feel okay doing that because if I triple both of those, that's going to get my silver to be 3 and nitrate to be 3. And now I've got my silver. Oh, sorry, that's supposed to be silver plus. Now I've got my silver matching, my phosphates matching, so that's looking pretty good. The thing that's not matching is the nitrate and the potassium on the product side. But you notice they need the same number now, and they're both the same number to begin with. So if I just put a 3 out front here, that will get my nitrate to 3, because I'm putting a 3 here effectively, and a 3 here effectively. And it gets my potassium to 3. And now I've got the same number of each atom and each ion on the product side and the reactant side. So this is a balanced chemical reaction. And that's really the essence of balancing a chemical reaction, is making it so that we're not creating or destroying atoms. We are only keeping track of all of them. So I saw the question, why don't we have a subscript 3 here? Right, when we write this K3PO4, let me switch colors real quick. Why don't we have a subscript 3 there? When we write this K3PO4, we have to recognize that this is an ionic compound. And what it's really representing is like a K plus with a PO4. I'm not going to draw the Lewis structure because it's going to take too long. But we've got our PO4 3 minus, and we've essentially got 3 K pluses being attracted to it through ionic bonding, right? If I wrote something like K3, like this suggests that K, those 3 Ks, those 3 potassiums are somehow linked to each other, right? And what I'm trying to communicate is this ionic compound here. So it's not really a K3. It's only K3 in the context of it being an ionic compound. The K3 is only when it's being 3K plus is being attracted to phosphate. This was actually, there was a question about this on the exam because we had that problem of Cl2 versus Mg Cl2. Ooh, that's weird too. Where the main thing that we wanted to recognize was the fact that this is covalent bonding. That is a covalent bond chlorine to chlorine. This, on the other side, this is ionic bonding. And that ionic bonding is going to be different than this covalent bonding. And recognizing the fact that one is covalent and one is ionic is kind of the key point to recognizing how it's going to dissociate in water. And it also will make some sense if we looked at the net ionic equation, which we can look at now that it's balanced. So if we looked at the net ionic equation, it might make a little bit more sense. But anything that's aqueous, we've identified as disassociating in water. So we're going to take those things and we're going to split them up. So that coefficient of 3 is going to give me, let me just label this real quick. Right, so that coefficient of 3 is going to give me 3Ag plus aqueous plus 3NO3 minus aqueous plus 3K plus aqueous plus PO4 3 minus aqueous. Let me put a space here so it looks like that. Let's try this. Right, so that is going to be really what we have on the reactant side. Breaking apart to ions. And so the fundamental recognition here is that this subscript on the K3 is representing those 3 ions. And when we put it into solution, it doesn't say K subscript 3, it becomes 3K plus, recognizing that we've got 3 potassium ions. We could have 3 potassium ions associated with phosphate, or we could have 3 potassium ions floating around in water. And so the way we write those two things is different, but it's still 3 potassium ions total. We can then go ahead and look at where this goes. The Ag3PO4 is going to stay solid, right? We don't break up the solid compounds in our net ionic. And then we're going to split up our 3K plus aqueous to represent the fact that there's still 3 potassium ions floating around a solution. And we've got our 3NO3 minus, also aqueous. And to get it to really net ionic, we would cancel out those things that are same element, same charge, same state of matter. So the nitrates would cancel out, the potassium ions would cancel out. And we just have 3Ag plus PO4 3 minus goes to Ag3PO4. And kind of the most important thing in doing this is kind of really recognizing this idea of covalent versus ionic and how the molecular formula translates to ions in solution. And I think maybe that's where you are getting hung up more, right? This is a place where a lot of students get hung up, and that's why I've done a couple examples about it in class. I had it on the midterm, recognizing that Cl subscript 2 could mean chlorine gas with a covalent bond, or it could mean chloride ions ionically bonded to a cation. So that subscript has a particular meaning to it, and recognizing that meaning is a big part of balancing chemical reactions. Now, just doing one problem is usually not enough to really understand everything that's going on. So let's look at more balancing as we continue working on problems. At this point, we have done balancing reactions, but we're going to keep balancing reactions. And I'm going to remove, awkwardly, I'm going to remove reverse through the list, since reverse through the list is kind of in time order. So let me pull up 8.1 real quick. And if anyone is time crunched and needs their question done sooner, just let me know and we can do it sooner. If you've shown up while I'm working on these problems and you have a Okay, so here we go. We're looking at 8.1 number 10. And I'm going to show you the problem real quick. So this is acetic acid reacts with sodium carbonate to produce sodium acetate, carbon dioxide, and water. How many milliliters of acetic acid are required to completely react a certain mass? So let's go ahead and look at that problem. Back over here. So we got to do a couple things to do this correctly. Right? This is looking at stoichiometry, of course, which means first thing we have to do is balance a chemical reaction. So let's go ahead and get our chemical reaction. We have to know what acetic acid is. CH3COOH. Well, capital H. That's going to be aqueous. We're going to react it with sodium carbonate. And I am not putting the correct thing right now. We'll deal with that in just a moment. Doing that on purpose as a teaching moment. And then we're going to do a flip-flop. Now, the thing that's weird about this flip-flop is I'm going to be flipping this H. And there's actually several different ways people write acetic acid. This is the way I usually write it, but you'll also see it written as H, C2, H3, O2. Right? And they write it this way, again, to kind of accentuate the fact that you've got, instead of having the H over on that end, you've got the H over on this end. And then there's even a third way when people get really lazy with this or really shortcutty with this. They'll do it like this, HAC, where that AC means acetate anion. And so I'll go ahead and define over here real quick. AC minus means CH3COO minus, right? That's the acetate anion. That's the definition I'm using. But you notice it makes it really easy when we do it this way, where we just call the acetate anion one thing. It makes it a lot easier to see the flip-flop that's going to happen for us predicting our products. That was weird. Okay. So I'm going to do my flip-flop. I'm going to predict that I'm going to make sodium acetate, and I'm going to make HCO3. Huh. Getting a weird dinging noise now, but that's okay. Now, the compounds that I have written here are not actually good compounds. So I have to do my whole charge balancing check to make sure I'm making good compounds, just like I did last time, anytime we're drawing chemical reactions. So I look at this and I'm going to be checking my charge balancing. H is a +1, acetate is a -1, that's looking good. Sodium's a +1, carbonate's a -2, so that's not looking good. Sodium's a +1, acetate's a -1, so that's looking okay. Hydrogen's a +1, carbonate's a -2, that's not looking good. Right, those aren't charge balanced. Pretty easy to fix the charge balancing. I put 2 sodiums in, I put 2 hydrogens in. Now I've got charge balanced. The problem here is now I've got a compound that's unstable in my chemical compound here. Carbonic acid will decompose, and it'll decompose into CO2 and H2O. And that just naturally happens. It's one of the only special examples of something that's unstable that I've asked you to just remember this quarter. which is the fact that carbonic acid decomposes. So that gives us, and also it's kind of given in the problem. I'm trying to do it, a long educational way, but it tells us carbon dioxide and water are products. It tells us the products already. So I can go ahead and write my balanced chemical reaction now. It's going to be HAC plus Na2CO3 plus, that's plussing, goes to NaAC, get my states of matter in there. Plus H2O plus CO2. And this is that typical chemical reaction we've done that bubbles but doesn't create hydrogen gas. I still haven't actually balanced this. So I've got 2 hydrogens on my product side. I've got 2 sodiums on my reactant side. So we can fix this pretty easily. Again, at this point, I don't want to change subscripts. All of my compounds are stable, charge balanced. So I only want to change coefficients at this point. To get my 2 hydrogens, I'll put a 2 in front there. So that gives me 2 acetates and 2 sodiums. So to fix the 2 acetates and the 2 sodiums, I put a 2 in front of the sodium acetate there. And now I'm balanced. Double checking. That looks good. Now we can get onto the actual stoichiometry. Step 1 for stoichiometry is write the balanced equation. Step 2, calculate reactants. Step 3, limiting reactant. Step 4 is react and calculate the products. Interestingly, this problem is actually not asking us to calculate the products. This problem is actually just asking us to think about the reactants. And we've got this special phrase here to completely react, right? That's going to be one of those phrases, like the other ones we've seen. We're going to have moles of acid equal to moles of base times a mole ratio. So we want to have our moles of acid equal to our moles of base times the mole ratio. And that's what that phrase completely reacts kind of clues us in on. So our moles of acid, now we can start kind of calculating these things and trying to think about what's going to happen here. Our moles of acid, we're being asked a milliliters and a molarity, and we're given a molarity. So that's going to be one of our 2 important equations that I keep writing down. Molarity times volume equals moles. And then we've also got 100 grams of sodium carbonate. That's going to be the other one we use. Mass times 1 over molecular weight equals moles. These 2 equations are wildly important, right? Part of the reason I talked about them back in week 2, and then I keep bringing them up, we've used them a couple times throughout the quarter, is because this idea of measuring moles is difficult. So we put it in terms of something that's easy to measure, either volume or mass, which are easy to measure. So we can use this conversion of molecular weight or molarity to get us to a number of moles. Now what that means is over here in this idea of moles of acid equals moles of base, I'm going to do a molarity times a volume is equal to a mass times 1 over a molecular weight times a mole ratio. And then I just start plugging in the different numbers I know. I know the molarity of my acid is 0.054. I know the mass of my solid is 100 grams. Should put units on this too. My volume is precisely what I'm supposed to be figuring out, so I'm not going to know that. My molecular weight for sodium carbonate, I can pull up my periodic table again. And I can look at sodium carbonate, and I can calculate the molecular weight of that. It's like, give me a moment. Unless somebody already has it to help me out. 3 plus 2 plus 12 plus 16 times 3. 106. So we get a molecular weight of 106. I can plug that in here real quick. That's going to be grams per mole. Mole would be on top. Make sure that division sign is really easy to see. And then I need to figure out my mole ratio. So I'm looking here, and I'm going to have 1 mole of base for 2 moles of acid. So my mole ratio of acid to base, right? I want my 1 mole of base on bottom. So moles of base cancel out. I'm going to have 2 moles of acid used for every 1 mole of base. Where I'm just using the word base in this situation, it's the carbonate that's behaving like the base. I'll add that definition up here. Right, so base is the carbonate. At this point, I'm going to write this down a little bit simpler. Since we've got all of our units worked out correctly, it's just going to be 0.054 times V is equal to 100 times 2 divided by 106. And oftentimes when we get down to these mathematical expressions, people are like, wow, that's it? And it's like, yeah, sure, that's it. 0.054 V equals, and we can even rearrange this and we can say V is equal to 100 times 2 divided by 106 times 0.054, put parentheses around that, and that's it. That's it, right? And I say that's it, but we have to recognize that mathematical equation. You can all multiply, divide, and things like that. But getting that mathematical equation that's easy to solve took a lot of understanding. We had to understand how to write a balanced chemical equation. We had to understand how to interpret the words such that we could make sense of what was going on. We had to figure out all of these little details to get to this simple mathematical equation that works, right? If you drop someone who's really great at math into a problem like this, they wouldn't be able to do it because they need to have that real world context and that real world understanding of what do these different terms mean? How do these different terms relate to what we are trying to understand? Questions? Again. Okay, so moving on to these questions from 9.1. 9.1, this is a set of questions that's relatively challenging to approach. So if we're looking here, number 16 is saying for the next several problems, determine the concentration of the ions in the reaction of the previous problems. So we need to be able to do all of these previous problems. Oh, it's just number 14. So nope, maybe not as good as I thought. But it's going to be this idea of ammonium carbonate with silver nitrate. That's going to be used for the next several problems. We're going to determine the grams of precipitate produced. This is pretty similar to looking at number 2, where we've got this ammonia reaction with oxygen to produce carbon monoxide. I'm going to go ahead and do number 16 first. Sorry, I was confused about which thing I was doing. But let's go ahead and look at number 16. I think number 16 will also help elucidate what's happening in number 2. So we're going to use number 14 to solve number 16 to 17 and 18 and 19. And this gets to one of the details that I was previously talking about in class yesterday, where we have to actually think about how things exist in solution. So we've got two different parts to the question. We're going to ask, what's the amount of grams produced? And then we're going to ask for the concentration of NH4 in solution after reaction. Okay, so first thing we have to do, right? It's a stoichiometry problem. So we're going to go ahead and write a balanced chemical reaction. We've got NH4CO3. I know that's going to be aqueous, so we'll write that for now. We've got AgNO3. I know that's going to be aqueous. That thing is going to mix. And it doesn't tell us what products we're going to make, so we have to do our own flip-flop. NH4 ammonium is going to be our cation. We'll switch that with our Ag, which is our other cation. So we're going to AgCO3, and we're going to get NH4NO3. Do our charge checking to see if our compounds are good. Ammonium is a plus, carbonate's a -2. Ag is a plus, nitrate's a minus, Ag is a plus, carbonate's a -2, NH4 is a plus, nitrate's a minus. So from this, I can tell I need to fix a couple things. First, I can tell that this is going to be aqueous, and my ammonium nitrate is already charge balanced. I can also tell my ammonium carbonate, I'm going to need 2 ammoniums to charge balance that. And so I put the parentheses around the ammonium and the 2 outside the parentheses to say I've got 2 of that cation there. My silver nitrate looks good. Oh, over here, my silver carbonate, I'm going to need 2 silvers to create that charge balancing. Then I can go ahead and balance my coefficients and see what's going on here. I'm going to need a 2 in front of that. So I got 2 silvers and 2 silvers. Now I've got 2 nitrates, and I've got 2 ammoniums on my reactant side. So just a 2 there. Now I've got my 2 ammonium, sorry, and my 2 nitrates. So that should be a balanced chemical reaction. I fix my subscripts to make sure I've got good compounds. Then I go ahead and I check my coefficients to make sure I've got the same number of cations and anions on both sides. To check what's going on with that silver carbonate, I check my solubility information, and I can see here insoluble ionic compounds number 2, carbonates are insoluble. There's a few exceptions, but silver is not one of those exceptions. So this is going to form a solid. Now I can go ahead and do my table method, thinking about where I start, how many moles I start with, what happens during the reaction, and where I end up. My NH4, let's go ahead and think about this real quick. I'm given a volume and a concentration, and a volume and a concentration. So I'm going to use that molarity times volume, one of my 2 really important equations. There's so many important equations, but this one just keeps coming up over and over again. Molarity times volume equals moles. Keeping in mind that the typical units here is moles per liter. So to get this to work out, I'm going to want my volume in units of liter. So this 50, I'm going to divide by 1,000 in order to get the correct units. So let's go ahead and calculate the moles we have for each of these starting materials. My ammonium carbonate is going to be 50 divided by 1,000. That's going to get me my 0.05 liters. We can even do it like this, 50 milliliters times 1 liter divided by 1,000 milliliters. Right? I'm hoping this conversion is fine for everybody, so I'm just going to kind of get rid of that for now. I'm going to have my 0.05 liters. I'm going to multiply by my 0.25 moles per liter. And that's going to get me my starting amount there. Of 0.0125 moles. I do a similar but different calculation over here for my silver nitrate, which is going to be 0.06 liters times 0.3 moles per liter. And that's going to get me a different number. .018 moles. Over on my product side, I'm starting with 0 solid, and I'm starting with 0 ammonium nitrate. Not starting with anything on the product side. A little wiggle there so I can tell the difference. So that's what I'm starting with. And now I have to figure out what the limiting reactant is. Do me a favor, real quick in chat, 1 through 5. How are you feeling about identifying limiting reactant? Most of you are feeling pretty good. 4s and 5s, great. So we can take a look at this. I'm seeing a couple of people showed up. The list of problems we're working on in the top left. If you want another problem on there, just throw it in chat and we'll get to it next. Everyone's feeling good about identifying limiting reactants, so I'm assuming that you all can look at this and you can recognize that silver nitrate is going to be the limiting reactant. It's the bigger number, but we've got that coefficient out front, and it's not twice as big. So even though it's the bigger number, it's not big enough to be in excess. Then when I go to my react step, I'm going to have minus 0.018 times my mole ratio, which is going to be a 1 to 2 mole ratio. I'm going to have minus 0.018 times my 2 to 2 mole ratio. Over here on product side, I'm going to have plus 0.018 times my 1 to 2 mole ratio. And then I'm also going to have plus 0.018 times my 2 to 2 mole, whoops, not 2 to 5, 2 to 2 mole ratio. Where again, the mole ratio is the ratio of the component we're looking at to the limiting reactant. So my limiting reactant coefficient is always on bottom of that fraction. Then I can go ahead and do my math in each column. And we have to do this in order to get to number 16. We have to finish number 15. So I hope people are okay doing number 15. We kind of need to. So when I look at this, that's going to be 0.009. That's going to be 0.0035. This one is going to be 0 excess. This is going to be 0.009 moles reduced. And this one is going to be 0.018 moles reduced. And that's all just getting it to the point where we can even start to think about number 16. So there's our different math associated with it. We can see here I've got some ammonium and carbonate left in solution. Here's the interesting thing that we have to think about to really make sense of what's going on here. This excess ammonium carbonate is actually going to be ammonium, and it's going to be carbonate. Let's see here if I can do this thing. No, I'm on an old version of this, which is really frustrating. Let me just move this over. Whoa, not what I wanted to do. Move this over here so I've got a little bit more space. Ammonium and carbonate. And because of the ratio of 2 ammoniums for every ammonium carbonate, this will be 0.007 moles. And this will be for ammonium, and this is going to be 0.0035 for the carbonate. Over here, this has nothing left, so we don't worry about it. This one is actually going to translate to some amount of ammonium, some amount of carbonate. I don't need the coefficient of 2. The coefficient of 2 is taken care of up here. So I don't need that coefficient of 2, and I'm doing this as just this 0.018. So I'm going to have 0.018. Again, this is moles of ammonium. And I'm going to have 0.018. That's a weird 8, but trust me, moles of nitrate. And those will all be in solution. I don't need to worry about the solid. The solid is solid. It's not going to be in solution. It's going to sink to the bottom. So one of the first things that you can notice here is how many silver ions do I have in solution? Well, I don't have any, right? All of the silver is ended up locked inside of the silver carbonate. So there's no silver ions in solution. Then we can say, okay, well, what's the concentration of carbonate? The concentration of carbonate, I can figure out just from this one number here, since carbonate is since there's only one place where carbonate is existing, I can just take this 0.0035 and from my definition of molarity in the top corner, right, this thing up here, I can rearrange this equation to say moles divided by total volume is molarity. And I can rewrite this thing to be 0.0035 divided by my total volume. This is the other part that really messes people up. My total volume is going to be 60 plus 50. So that's going to be 0.11 liters, right? It's going to be this 0.06 plus this 0.05 to get my total volume. And that will get me my concentration of carbonate, which is going to be 0.018 0.0318 molarity. That's for carbonate. And I decided to do carbonate before we did ammonium because it's a little bit easier. And it's kind of funny because always in week 10, I'm reminded that I should change the order of the problems on this assignment so that it's not the hardest one first, because ammonium is the hardest one. And every year I'm like, oh, I'll remember to do it later. And every year I forget. Here we are, forgotten again. Maybe I'll remember this time. So now when we look at this, we can do the same type of logic, right? We can do the exact same calculation. Nitrate's super easy. When we do ammonium, I have to take this 0.007 excess plus this 0.0018. I have to add those two numbers together to get my total amount of ammonium in solution. to calculate that concentration of ammonium. So that's going to be, oh, math is hard, 0.025? Is that right? That's my moles of ammonium. It's still the same total volume, so I divide by 0.11 liters, and that should get me the concentration. Again, we end up in this position where it's like the answer is 0.025 divided by 0.11. That's a really simple calculation to do, but it's really important to recognize that we had to do a ton of work to get there. The excess, and maybe I made a mistake in my calculation, was doing the math down like this. So let's pull up my calculator real quick. Not the best calculator to use, but to get my moles excess, I did my 0.0. Oh, I forgot my numbers now. Where's my whiteboard? Can't see my whiteboard. But I'm just punching into the calculator. So I'm doing 0.0125 minus 0.018 divided by 2. And that gets me to 0.0035. I did the calculation correct. Had me doubting myself for a moment. So yeah, I like to do the math in the column way where I do my starting amount, then my reacting amount. So it's 0.0125 minus the 0.018 times a half. And that gets me by 0.0035. Instead of doing math in a single line, I do math in columns. Two, two, seven. And that gets us the right answer. I had to double check and make sure I got the right answer. Questions about this problem, you can put it in chat or you can unmute and ask either way. In that case, we'll go ahead and move on. Problems we're working on. Got that one, got that one, got that one. 9.1 number 2. I feel a little bit bad for 9.2 number 13 because I think that was the first question asked and I'm getting to it last. I'm sorry. I hope you don't mind. Let's go ahead and look at 9.1 number 2. I've already got this problem up. So this is one looking at this calculation, and we're just trying to get the mass of carbon monoxide produced. And I find that most people are actually really close to doing this problem correctly, and there's a few common mistakes. That's not what I do. And there's a few common mistakes that are happening. And we'll see what we can do to address those. Wow, it's really not letting me do the thing. There we go. Weird. Okay, so we've got a sample of ammonia. It's reacting with oxygen. It's a combustion reaction. I feel like you're all going to be pretty good at this point. So I'm just going to start cranking through it. I'm going to try to talk a little bit less. Same type of thing we've already done, right? Start with getting our balanced equation. It tells us what the products are. That's pretty common when we're dealing with redox reactions, because sometimes redox reactions are difficult to predict in terms of products, right? Why do you make a nitrogen monoxide instead of a nitrogen dioxide? What other kind of products Why don't you make dinitrogen tetroxide? Different redox reactions could do those different things. Then I have to go ahead and balance this. Um, I'm just kind of going through it. This one's a little bit tricky to balance, so maybe I should talk through let me talk through my logic real quick on balancing this, because there's kind of a process you can think about. So I'm just going to grab pen real quick. My first thought was, I know I need an even number of hydrogens because I've got an H2 over there, so I just doubled this, which is going to double that. And then I was like, cool, that gives me 3 hydrogens. That's going to give me 6 hydrogens, so a 3 there. But then I noticed, wait, is that going to be okay? No, because that's 5 oxygens, and I've got an even number over here. So I was like, cool, I know all of those numbers need to keep the same ratio, so I'm just going to double all of them, so I get 4, 4, and 6. Now that's going to give me 10 oxygens, right? Before, when I had 5 oxygens over here, there was no way to balance it with the O2. So I doubled everything. So I've got 4 nitrogens, 4 nitrogens, 12 hydrogens, 12 hydrogens, and now I've got 10 oxygens, which is an even number, and I can slap the 5 in there to get that balancing. So since that one was a little bit trickier with balancing, I wanted to talk through it real quick. 4, 5. 4, 6. I'm going to go ahead and delete all of that. We're done with that now. If at any point you need me to slow down, just holler. I'm going to do my start, reaction, end. I'm going to have 2.00 divided by 17. I'm going to have 4.00 divided by 32. Both of those numbers are coming from my other really useful equation, which is mass divided by molecular weight equals moles. The other equation we use to get our number of moles. So I go ahead and punch those into my calculator real quick. You should all be calculating along. Don't make me do all the work. Also, don't trust my work. I'm trying to go way too fast. 0.117. 0.125. 0. 0. Again, I'm just going to give myself a little visual break because it helps my brain a little bit. Products, reactants. Here we go. Okay, now in my reaction step, again, we're all saying we're really good at limiting reactants. This one, it turns out that the oxygen is the limiting reactant. It's the bigger number, but it's not big enough, right? If I do this kind of like 5/4 to 4/5 comparison, the 0.125 is not big enough. We can also do the guess and check method where I'm just like, I don't have time to check, so I'm just going to pick one and make sure and see how it goes. So I'm going to have minus 0.125 times the mole ratio, which is going to be a 4/5. And I'm going to have a minus 0.125 times the mole ratio, which is a 5/5. And I'm going to have plus 0.125 times the mole ratio, which is 4/5. And I'm going to have plus 0.125 times the mole ratio, which in this case is going to be 6/5. That over a little bit. Make this line a little bit longer just for giving myself more space to work. couple other spaces there just to. Okay. Then I can go ahead and do my math here. Again, doing my math down the columns. So I'm doing this number minus that number to get that, this number minus that number to get that, doing math down this direction. In each of these cases, to get how much I have at the end of each case. So I'm going to have 0.017. I'm going to have 0. I'm going to have 0.1. And I'm going to have, this one I actually have to punch into the calculator. 6.5, 0.15. So that's my amount created in each case. This is going to be moles, 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 moles of each thing in each column. So this number here is going to be my excess NH3. This number here is going to be my NO produced. The common places where people have mistakes is they mess up the balancing. That's kind of one of the big places where people make a mistake. They mess up the balancing. So that's place kind of one. They mess up this balancing. Another common place where people make a mistake is they identify the wrong limiting reactant. They just take the smaller number, and that's not the correct thing to do. You have to take that mole ratio into account. The last place where people, I've seen a less common mistake is they use the wrong molecular weight for nitrogen monoxide here. So our last step here is we have to do 0.1 moles of nitrogen monoxide times the molecular weight of nitrogen monoxide. And if we look at the periodic table here, our molecular weight for nitrogen monoxide is going to be 14 plus 16. That's just going to give us a molecular weight of 30-ish. So what we're going to do is we're going to have 0.1 moles times 30.01 grams per mole. And that should get us 3.001 grams. If you put in 3 grams, it will probably work as well. Those are the common mistakes, is the limiting reactant. Let me mark the third common mistake. Less common, but I've seen it happen. Identifying the wrong limiting reactant, getting the wrong balancing coefficients, or pulling the wrong molecular weight for nitrogen monoxide. Okay, so a further question on top of this one, which I think is the next question in the problem. Let me just double check. It's number 5. So let me go ahead and copy the text for number 5 if we wanted to think about the kind of next further thing. I haven't had anyone ask me about this one yet, so let's see if I can get it correct. Right, and this is a kind of interesting thing, right? This was something that I was recommending a lot when we were talking about getting ready for exam 2. We can also talk about it getting ready for exam 3, which is, now that we know how to do the problem, can we think of what the next most difficult problem would be? So here's the question. How many more grams of the limiting reactant would we need to use up all of both reactants? So what we can do here is we can take our excess reactant, 0.017 moles of NH3, and we can say, how many moles of O2 would I need for that? So I'm going to multiply, I'm going to do essentially the flip of the limiting reactant. So I'm going to multiply by 5 moles of O2 for every 4 moles NH3. And that's going to get me how much more O2, oil with an M. That will get me how much more O2 I would need. So 0.017 times 5 divided by 4. So if I had just 0.2125, oops, that's not. So that would be how much more O2 I took that excess amount, I used the mole ratio, so I got that more moles of O2, and then I can go ahead and multiply by the molecular weight, and that will get me the grams more I would need. So I take that number, multiply by the molecular weight of oxygen, so that's going to be 0.68 grams more needed. We could also translate this to total grams needed. And so that would be, how can we check if this is the right answer, essentially? And then I saw someone raise a hand and put it down, but put something in chat if you'd like. So let's do a quick check to see if that's the right answer. So all I'm going to do for this check is I'm going to come back up to this, where I originally did the problem, and I'm going to change this to 4.68. I'm going to calculate how many moles that is. I'm essentially going to redo the problem with this new number, 4.68 divided by 32. That's going to get me 0.14625. So it gets me a slightly bigger number, 4625. But now if I put that number in here, myself a little bit more space. Now, if I did this correctly, when I do this calculation down here, that should get me 0 excess reactant. So both things, the language I use is both things are limiting. And when I multiply that through by 4/5 and do my subtraction, I indeed get 0 left over. So if I did this situation where I had this increased mass, I plug that in there, you can see I end up with both things running to 0. That would be, the language I use is if both things are 0, both things are limiting. And during my reaction step, I could use either number and get the same answer. Now, I didn't redo the rest of this, right? I should redo this one. I should redo all of these for this. But that is just a quick way to check if the answer I got was reasonable down here. And it sure does check out. That looks good. So that's number 2 and number 5. Questions on that before we finally move on to number 13 on 9.2? And whoever asked number 13 on 9.2, thank you so much for your patience. Everyone should applaud you. Okay. Let's go ahead and take a look at number 13 on 9.2, which I thought I had set up here. There it is. Oh, okay. Let me start by saying I will likely not ask a problem this difficult on the final exam. Right? That's part of why I call this a challenge problem. And this is one of those conceptual ideas that we were talking about in class yesterday, at the beginning of class yesterday, where we've got 2 reactions in one container. 2 reactions, 1 container. we got a solution. Now, I tried to make this a little bit easier because I put it in terms of moles instead of grams, giving us less things to convert. We've got a moles of acid, and that moles of acid is a mixture of two different acids with two different mole ratios. It's going to react with a certain amount of sodium hydroxide. This is a tricky one. Okay, so the first thing we need to realize is that we've got two different chemical reactions going on. We're going to have HCl plus NaOH as one of our reactions, going to NaCl plus H2O. And then we're going to have a second reaction, which is going to be 2HCl plus H2. Whoa. Nope, not 2HCl. H2SO4 plus 2NaOH. There we go. Goes to Na2 SO4 plus 2H2O. I'm going to do a little bit. I should have my states of matter here for everything. That's aqueous. That's aqueous. I'm going to put some extra steps in here to get these things to line up. That's aqueous. That's aqueous. NaCl is aqueous. In fact, here, the products don't matter besides the fact that we need to balance our chemical reaction. That's liquid. That's liquid. And our common reactant here, this is a tough one. Okay, our common reactant here is going to be the sodium hydroxide. So we're going to use that important kind of concept that we used before, right? Because it says equivalence point, stoichiometry still works. So my moles of acid is going to be equal to my moles of base reacted times the mole ratio, right? The same concept still applies. But now I've got to be a little bit more careful here. So I'm going to have my moles of HCl times a 1-to-1 ratio plus my moles H2SO4 times a 1-to-2 ratio is equal to my moles NaOH. And the reason that works is, again, because we're specifying it's at the equivalence point. That's what lets me say those things are equal to each other. So let's plug in the bits we can, the bits we do know. And this becomes a 2 equations, 2 unknown problem. And I told you yesterday in class that I wouldn't ask you to solve these types of problems during a quiz or exam. But in the real world, in real life, you're going to end up with situations like this. So pieces of information that are useful, 100 milliliters doesn't really matter in this case. I've got my total moles here. I've got my moles of sodium hydroxide here. I'm going to be using that important equation, molarity times volume equals moles. So let's plug in a few pieces of information we know. For this situation, I'm going to have X moles of HCl. I don't know how much it is, but I know it's going to be some value of X. I'm going to have Y moles of H2SO4 times that 1-to-2 ratio. Oh, do I have my mole ratio set up wrong? I do. Let's be careful about this. Let me do a quick aside to make sure I got my mole ratio correct. Right? So being careful here. I know I want this to be equal to moles of sodium hydroxide. Right? This is a common mistake, and I think I made a mistake, so let's fix it. Now, if I've got it in moles of H2SO4, right, The HCl 1-to-1 ratio doesn't matter. If I got it flipped upside down incorrectly, no one can tell because it's 1/1 or it's 1/1. But this 1/2, this actually matters. So I have to make sure I've got it right. If I have H2SO4, I'm going to want to get my coefficient. I want this sulfuric acid to cancel out. So I want my H2SO4 coefficient on bottom, and I want my NaOH coefficient on top. So that way, when this cancels out, H2SO4 cancels, and I've just got sodium hydroxide left over. If I'm doing it that way, I'm going to have 2 on top, 1 on bottom. Ooh, I did get it wrong. Fixed. Important detail to watch out for. Let's fix that. 2 on top, 1 on bottom. Right? When we get used to this, even me, right? I get used to doing these problems. I'm just clicking through in my brain real quick. I'm like, oh, it's a 1-to-2 ratio. If you don't slow down, if you don't have the ability to slow down and do this type of unit analysis to make sure you've got your mole ratio correct, you're going to be banging your head against the wall. You're going to come to me and ask for help, and it's going to take me like 15, 20 minutes to find your mistake because it's such a subtle mistake, but it's so important. And this is part of why I'm trying to do this quickly because I'm typing it out. I'm not on the whiteboard. I'm not on like a nice like digital board. So I'm trying to type things out short, and I'm not keeping track of my units, and that almost got me in big trouble. This is part of why I say always write down your units. Me trying to do this short almost ruined everything. Okay, but we got it fixed. I can get this check out of the way now that we fixed that. Can I get that check out of the way? Okay. And then the last thing that I want to put in this calculation is the fact that I've got my 0.05 times 0.2. I think that's 0.1. I'm going to double check 0.05 times 0.2, 0.01. Perfect. So I can put in 0.01 moles of sodium hydroxide. Now, I don't know what amount of this sodium hydroxide reacts with the sulfuric acid or the HCl because I don't know how much HCl there is. I don't know how much sodium, I don't know how much sulfuric acid there is. What I do know is that my X moles of HCl plus my Y moles of H2SO4 will add up to a total of 0.0, whoa, that's not how you write that, 0.07 moles total. And now we're at the point where we can do 2 equations, 2 unknowns, which last night during class, everyone was like, don't make us do that. That's the worst. But this is the point we'd get to, and we could do 2 equations, 2 unknowns, right? I can rearrange this. I can substitute and solve. Do me a favor, do a quick reaction of like a thumbs up if you want to see me keep doing this problem. Like I said, we're not going to do one of these problems on the exam, but if you're just curious and you want to see it, do some kind of reaction. That's that's 2 people reacting. Okay, we'll do it. Let's just do it real quick. Okay. So 2 equations, 2 unknowns. How do we solve? Right? I'm going to start by just rewriting this into a purely mathematical way. We've done our unit analysis. We've got everything correct. We're going to have x plus 2y is equal to 0.01. Right? Forgetting all the units, just keeping the important parts. And then we're going to have x plus y is equal to 0.07. And normally when I write this down like this, people are like, oh, that's easy. But let's go ahead. Let's keep going with it. I'm going to rearrange this a little bit. Right? So this is actually the problem that we have to solve. Where I'm going to go ahead and do x is equal to 0.07 minus y. And then I can go ahead and do a substitution. Let's do it up here. Then I can do a substitution of 0.07 minus y plus 2y is equal to 0.01. Right? So what I did was I just rearranged this x, plugged it in there, and that gets me this equation. That y cancels out. I'm going to get y. I'm going to subtract the point. Why is this freaking me out? Did I make a mistake someplace? I made a mistake someplace. Hold on. You're all supposed to stop me when I make a mistake. Way back here. Let me mark it in red since I made a mistake. Way back here, I made a mistake. And it didn't matter until now. And I'll just highlight it over here. It was a kind of silly thing. It's the same type of mistake that you would all make. And I knew it was a problem over here when I was getting to solving this thing because I was like, I'm about to get a negative moles. I must have made a mistake. When I did this, I did 0.05 times 0.2 equals 0.01. And probably from me writing that down, you can see the mistake I made, right? Right? I just threw an extra decimal place in there for no apparent reason. Now, I could catch myself as I went to try and solve this, and y'all heard my brain stop in the middle of doing the problem, I think, right? As soon as I was looking at solving this, I was like, wait a minute, I'm going to get a negative value for my moles. I know I can't have a negative value for my moles. So I started looking for my mistake, right? And having that level of awareness is really powerful, right? Being able to do the calculations right the first time and not make any typos, sure, that's great. Being able to recognize an answer doesn't make sense is actually more important. So being able to recognize that this answer doesn't make sense was actually the essential part here. But now I can go ahead and fix this. I found my mistake. I can fix it. That's going to be 0.1. And now I can go ahead and solve this out. I'm going to end up with y is equal to, one of those cancels off, subtract it, is equal to 0.03. After I get y is equal to 0.03, then I can go ahead and calculate my x value, because I know x plus 0.03 is equal to 0.07. So that means x must be equal to 0.04. Let's see, I'll do it in this blue color. So after I had this y value, I plug it back in over here, and that gets me down to this thing. Two equations, two unknowns. Questions about that? Again, this type of problem, I might ask you to think about this bit up here. I'm not going to ask you to do this bit down here. I might ask you to think about this bit too, but I'm not going to ask you to actually solve the two equations, two unknowns. I might just ask you to do the thinking steps. I don't see other questions coming in. I know there's some people who want to talk about grades and other things, so I'm going to go ahead and stop recording. I'll post this recording so people can look at it later, and we'll have a little bit of time for people to ask individual questions as